I've been working with GaN for 10 years or more, and I see a common pattern of issues that designers often have to deal with. And the purpose of this video then is to outline what are the 5 key areas to focus on for successful design when you're first using GaN. You know, if you're familiar with silicon but you haven't used GaN yet, this should answer a lot of questions and show you quickly how to get to a successful design. I'm going to go through number 1, making sure that you understand the device limits. Then there's a couple of topics here on gate drive. Make sure the gate drive circuit design is correct, and the layout, because really the layout is an important key aspect of the design. And then the other is commutation loop. So there's the gate drive loop, there's the commutation loop for high current. And then finally, thermal management, how to optimize that while not compromising the electrical design. So let's start out by taking a look at 3 different types, 3 different technologies of power transistor. The first one we'll look at is CoolGaN. This is a 55 milliohm transistor, and next to that in the center is the silicon equivalent CoolMOS that you're probably all familiar with. This is a little bit lower on resistance. It's the closest that matched in terms of overall capability. And then notice the silicon carbide, the CoolSiC, is a 60 milliohm device. The reason this was chosen at a little bit higher RDS(on) is because what really matters is not 25 degrees C. What matters is hot at like 125 C, and we'll look at that in a moment. So this is just the front page data sheet of these 3. Let's focus on the key parameters that most designers are looking at in designing power supplies. Starting with the RDS(on), now we're at 125 C, and you can see already that the silicon carbide and the silicon, the superjunction, are essentially the same. The GaN is a little bit higher here because it has a slightly stronger temperature coefficient. But these are all still in the same range. The next thing we look at is the reverse recovery, which is one of the key parameters why users are typically interested in using GaN, is because the minority carrier-induced reverse recovery is 0. There are no minority carriers involved. It's only the capacitance of the device that gives you any sort of measurable charge. Superjunction, on the other hand, is like off the charts, right? This is, 860 on a good day. This is at 25 degrees C. It's over 1,000 at hot temperature. That's why we don't use superjunction, where reverse recovery is important. It's just simply not suitable for that sort of operation. Silicon carbide is also very good. It's a wide bandgap semiconductor, but it does have some minority carrier charge. Very usable, though, with a small reverse recovery of 38 nanocoulombs. But here, GaN is the clear winner in terms of reverse recovery. And in a related, now if you look at the JEDEC definition of reverse recovery, it combines both the minority carrier QRR and the capacitive component. But you can see in all cases, the superjunction is the one with the really large charge here that's not going to be a good transistor to use for fast switching where the body diode matters. For the QoS of GaN, quite low, and actually the silicon carbide, latest generation, is also quite low. And then there's current. So there's the continuous rated drain current, ID, at 25 degrees C case, and then there's the pulse current, which is also at but the 25 degrees C case isn't really what matters. What matters is this is rated at peak TJ. So for the continuous, it's really all about the thermal performance, how big the die is, how good is the thermal conductivity. That's really what, this isn't an intrinsic device limit. On the other hand, the pulse current, this is where you have to start paying attention, especially with GaN, because notice that silicon carbide is up here near 100 amps, superjunction is up here near 130. GaN looks pretty good here at 60. It's still half of the silicon superjunction, but When you get up to even higher temperatures, as you'll see, this can drop even further. So you have to really pay attention to how much current can I really handle at the maximum operating temperatures. DI/DT, there are no limits on the wide bandgap devices. You can turn them on as quickly as you're able. With superjunction, again, because of this body diode dynamic performance, typically it's limited, and it's a pretty severe limit. And then finally, gate charge. This is again where GaN has an extremely low gate charge because it has a low threshold voltage and very low capacitance. Superjunction is quite a bit higher. Silicon carbide is not bad. It's in the same ballpark, especially when you consider that typically you overdrive the gate of the GIT. You deliver extra charge anyway when you first turn it on. We'll see that in the section where we cover the gate drive circuit. And then finally, this is really all about die size, die thickness, but the superjunction, being a very large transistor, has very low thermal conductivity. Silicon carbide is a small device, as is GaN, but SiC has a very good thermal conductivity. So there's a bit of a spread here. Let's next look at the gate structure and the differences between the so-called hybrid drain GIT and the Schottky gate. Most of the devices you'll see on the market today at any voltage are what's called the Schottky gate transistor. So both of these, no matter which gate structure it is, they're lateral devices. You have a source on the left side here, you have a drain on the right side, and a gate somewhere in the middle. The main difference is in how the gate metallization works. With the Schottky gate, you actually have two back-to-back diodes here. So when you run it on a curve tracer or try to drive it, it looks capacitive. It does have some tighter voltage limits. You have to pay attention to drive it at about 6 volts. Don't want to go much over 7. But you need enough drive. You can't, like with a regular silicon transistor, it's on 8, 9, 10 volts, and you can go all the way up to 20 typically. With GaN, and with any wide bandgap, really, it's limited, right? You want to be precisely at the right gate voltage, plus or minus 1. Because otherwise, either if you're too low, it's not on fully, or if you're too high, it begins to impact device reliability. Now compare that to the so-called GIT gate injection transistor. Here, the metallization is different, and you actually have a diode. So the gate is, when it's on, you're forward biasing a GaN diode at about 3.5 volts. So it's essentially a self-clamping structure. It's very hard to break the gate. It's an incredibly rugged gate. You don't care about overvoltage. It's not even specified on the data sheet. We simply tell you what current you can deliver, and the gate voltage is what it is. So you drive it with a current source in the forward direction, and it does require a continuous bias to remain on. There's also P-GaN here on the drain, and the combination of these two P-GaN structures helps to eliminate dynamic RDS(on), which is quite low. It's typically in the range of 2% for a GIT, whereas the Schottky gate high voltage devices can be in the range of 20 to 30% dynamic RDS(on). So one question that comes up is, why can't I just drive the transistor like any other MOSFET with a voltage? Why do I need current? The answer, it's a little complicated, but let's take a look at what happens if I try to do that. So knowing that I have a diode here that's at around 3.5, what if I say, okay, I'm going to drive with 3.4 volts, and then I'm on. As close as I can get. Here's what happens is, what matters is not the voltage between gate and source, but the voltage between the gate and the conducting channel below the gate. This is not necessarily at 0. It depends, right? If I have drain current flowing here through the channel, this voltage will be some positive value. If I have a lot of current, it could be like a volt. Conversely, if I'm going the other direction, in third quadrant conduction. Now this could be at -1. So here's the problem. Now, how do I correctly drive the VGS when I have this variable below the gate that I need? That's what I really want to drive. And it can vary by ±1. So I'm either going to be over voltaging or under voltaging, and there's no single value of gate voltage I can select that will properly bias this under all conditions. So the answer is drive it with a current. The diode sets the voltage. It is what it is. Just let it be there. And now the question is, okay, do I need a special gate driver to do that? No. You can use a standard off-the-shelf gate driver just like you'd use for silicon or an IGBT, for example. And we use a network here called RC network. And it's quite simple. It's really just a capacitor in series with a low value. So this might be, for example, 3 nanofarads, 5 or 10 ohms here. And this delivers a quick turn-on charge to get everything turned on properly. And you see that here. You get a pulse of current in the gate. Once this settles out, the time constant of that is like 30 nanoseconds. Then you are in the steady state region for the rest of the on period. And here you set this RSS value, by what's my VCC, what is this voltage, typically 3.5, and you then, use Ohm's law, figure out what do I need for RSS. And that sets the steady state current. And this you'll see is one of the common mistakes is to not have enough drive current. And I'll show you why in a little bit. And then to turn off, the safest way to turn off, especially in bigger, higher power supplies where you might have large transient currents, big device, we tend to use a negative bias here. It's not mandatory in every case, but it provides extra assurance that when the device is supposed to be off, that it stays off. This is what a common gate drive circuit looks like. So I'm using a standard off-the-shelf driver here. This does have a couple of cool features I'll mention, but it has bypass capacitors here. So I have +9 and -3. And then the Kelvin source here is my local common. That's what goes to the source, the Kelvin source of the transistor. And then here's the RC network. I've also included a connector here, this MMCX. This enables easy measurement of VGS on either the high or low side. So you wouldn't have to put this into production, but at least for initial testing, this is handy. And I'll show you in a different video the kind of probes that you would use and how you use this measurement point to make that measurement. There's also another diode shown here. Again, this isn't mandatory, but what this does is when I turn on, I mentioned, I discharge the capacitor into the gate. When I turn off, the discharge path for the capacitor is through this steady state resistor, 499 in this example. Well, that time constant's fairly long. It's a microsecond or two. So if I'm going to have a short off time, I want this capacitor to fully reset by the next cycle. I can do that by adding this diode, which will guarantee that I now have a very fast reset of the capacitor during the turn-off period. So this is kind of, we refer to this as our bulletproof gate drive circuit for the GIT. With these components, you're guaranteed to be driving it correctly. And now the question is, well, how do I power the gate driver? There's 2 fundamental methods. The most common for high power use is using an isolated DC-DC converter, right? This is a little power supply for the gate driver. It's an oscillator and driver, and then a little transformer and rectifier. There are different ways to do this. We have application notes that show more specific detail, but don't worry about those details right now. The important thing is that these are both floating DC outputs, so they can move up and down easily as the transistors switch. The other way, this is particularly popular in low-cost designs, let's say AC adapters, things like that, is what's called bootstrap power. And that's where you have a temporary energy reservoir here, this capacitor. When I turn on the low side, I bring this point to approximately ground, and I then charge up the cap. So this is during, when the low side is on. When the high side is on, this is then, reverse biased. Energy is stored here, and it provides power for my gate drive circuit. It's a nice, easy, low-cost way to provide power for the high side, and it's used commonly with traditional silicon or even silicon carbide designs. But there are a couple of important things to consider when looking at this method of powering. As I said, bootstrap, it's simple, it's low cost, a couple of components. But the other issue is that I don't have any VCC. There's no power when I first power up. I have to go through an initialization period to establish a charge. And during that time, there's no bias on that gate driver. So I need a gate driver, if I back up here, I need a gate driver that even when it's not powered, has the ability to clamp the VGS, right? Because I don't want this gate to turn on by itself due to external influence of changes in voltage on the bus, for example. So even with no power, the gate driver needs to have a clamp function. And that's what's unique about that 1EDB 8275 that I showed in the previous slide. It has a so-called fast clamp. It acts to keep the gate voltage at or below 1 volt, and it acts in 20 nanoseconds, so it's extraordinarily fast. The other thing is, with bootstrap power, you really can't do a negative supply. So if you need the negative supply, go with the isolated DC-DC. There are also duty cycle limits. You need time to refresh the bootstrap each time you turn on the low side. And if that's too short of a time, then you haven't fully recharged it, all right? Also, when the low side is on or when the low side is conducting, you're not always at zero. Could be -3 volts if you're in diode mode. Could be +1 if it's high current. So there's a lot of variability in the charge voltage you end up with. DC-DC, you don't have that. You have a very reliable voltage source. You can even regulate it if you want. So that's the advantage. The DC-DC method, you don't have to worry about initialization. It powers up right away, ready to go. There are no limits on duty cycle, and it's easy to create a negative bias when you need it. You can regulate them, and you can even add additional outputs if you need. So why not always do that? It seems to be the logical choice. Well, it does require more board space. You need a transformer to do this. It's small, but maybe typically gate drives are 6 or 8 millimeter kind of cores, but every square millimeter counts on a board. It takes a little more space, and it costs a little more because you need the oscillator, the driver, and the transformer. So now we talked about the design of the gate drive circuit and how to power it. The next thing is making sure that the circuit layout on the board is workable, that it doesn't create additional problems. Let's take a look at a traditional layout of a gate drive circuit that I see these all the time. First-time users with GaN will often do this. On the left side here, we see the gate drive circuit that we just talked about. So this is the gate driver U1, which is located here on the layout. The RC network we talked about, which is in between, and then the high side transistor. And here's gate, here's Kelvin source, and this is the body of the transistor here. Now, if we want to look at where current flows, let's look at turn on first. So turn on goes this way into the gate, then it comes back out and returns to the capacitor, right? Capacitor is always, the bypass cap is a part of the circuit. If I draw the same thing here on the layout, we're going this way into the gate, goes into the transistor, comes back out, returns here, okay? that's about as tight as I can get on a single layer layout. I can't move the return path any closer because I'd run into these components. Okay, now let's look also at the turn off path. Because remember, there are two gate drive loops, turn on and turn off. The turn off here, if I start at the gate, goes this way through the IC and back. Capacitor isn't involved at all, right? It's just this direct loop. You're shorting the gate source through the RC network here. So if I draw it on this path, it goes here, and then it goes to the ground here of U1, and then back over here. So again, you know, this is as tight as we can get on a traditional single-sided layout. So I said it's a typical but not very good layout. What makes this not so good? All the components are in close proximity to the transistor, right? Here's a transistor, RC network, gate driver. I can't get any closer. The paths are short and direct, and you can see there's no wasted space here at all. And finally, the return, the common, is as close as I can get. Or is it? I mean, that's this path right here. Is there a different way I can route this to improve the overall performance? And the answer is yes. And the key is that I need to go to the second layer. Before I show you that, though, let me point out that in this case, the second layer happens to be used. And that creates the second problem, is this entire gate drive circuit on the high side is sitting over a ground plane. So I'm going to have capacitive currents from my gate drive circuit to this ground every time I switch. So there's really two fundamental problems here. So let's get rid of that ground and use this space instead for my gate drive return path. Now layer 2, you can see here, is it's a plane. It's a copper pore underneath the entire gate drive circuit. And it's only 0.18 millimeter, right? Not 2.5, it's 0.2. So this is where I get the big benefit. And obviously it's exaggerated here in this expanded view, but you can imagine that the loop area here is extraordinarily small. So I get the best possible low inductance in my gate drive circuit, and I get the benefit that the copper pore gives me a Faraday shield for this whole circuit. So the same concept you're going to see that I just showed you for the gate drive will also be used in the overall commutation loop here for the main circuit. We'll look at that next. So one question that I've thought about is, why is it that on a circuit board, inductance always tends to be the biggest problem rather than capacitance? Especially because you have a planar structure, right? And usually flat wide conductors are typically lower inductance than than round, widely spaced. Moreover, the dielectric constant of the board material, it's in the range of 4 or 5. So that means that whatever capacitance I have between these large areas, these are like parallel plate capacitors with a dielectric between them. So it's going to amplify the capacitance by a factor of 4 or 5. So wouldn't that make capacitance a bigger problem? And besides, there's no permeability, meaning that I don't have the same effect for inductive effects. There's no ferrite or anything here in the board to enhance inductance. So, I've got all these parallel plate capacitors with dielectric, wide conductors. This should all point to capacitance being the problem rather than inductance. So let's look at some real-world numbers here, because I had to look at this myself to understand why is this, the case. So I took a power supply that we have, a 3 kW power supply. So the peak currents are on the order of 25 amps. It's a 400 volt bus. And I measured the inductances, the capacitances, and looked at the overall board layout to try to understand this. And remembering that I equals C dV dt, so on the capacitance side, what is the typical dV dt we get with these circuits? Well, In soft switching, it's typically in the range of 2 to 20 volts per nanosecond. Hard switching is quite a bit faster, typically like 50 or 60, ranging from 40 to 100 volts per nanosecond. The typical capacitance of that switch node that we looked at, it could be anywhere from like 5 to 50 picofarad. We'll say 10. If we use 10 picofarad and 60 volts per nanosecond as our example, typical value for this power supply, the current seen in this capacitance is only 0.6 amps. Don't really care, right? It's not a big deal, especially when we're talking that 20 or 30 amps is the peak current that we're dealing with. This is only a few percent of that, so it isn't really something to worry about. Now, of course, if the capacitance is going into a sensitive node somewhere, it means you have a bad layout. So yeah, you should worry about it then, but in a proper layout, that's not the case. Now, what about inductance? Remember V equals L dIdt. So again, what is dIdt? It's difficult to measure. You need a circuit set up with a shunt to be able to even measure this. Typically 0.5 to 5 amps per nanosecond in soft switching, and not a whole lot faster. It's a bit surprising, but even in soft switching, you need to clamp an inductive current that was following one path. Now you're commutating it to another path. These are still fairly fast current rise times. So soft switching doesn't always solve the LDIDT problem. The inductance in a power loop is in the range of 5 to 20 nanohenries. If it's more than that, you're in trouble already. Let's use 10 as our example, and I'll show you some examples of that. Now, if I take that 10 nanohenry, 8 amps per nanosecond that we just talked about, typical, I'm going to have 80 volts peak. So on a 400 volt bus, 80 volt overshoot, let's say, that's 20% of the bus voltage. It's 10x more in percentage here, right? So it's clearly a bigger problem, but the other issue is, where is this 80 volts appearing? If it's just overshoot on the commutation loop, okay, that's fine. But if it's in the gate loop, if any portion of that is in the gate loop, now you've got trouble, because a few volts in the gate loop make a big difference. And this is where understanding these numbers then help you decide how to prioritize your layout in terms of, where do I care about making low inductance and where do I not care? Remember that the half bridge that we keep looking at, this is the fundamental building block. And if you think of it as a two-port network where one side is the voltage port, you want to maintain a stiff, regulated voltage there despite whatever current is coming and going. And on the other side, this is a current port. This is where the inductor is. And I just have a steady DC current here despite whatever the transient voltage may be. So completely different way of looking at it. Here, I need to have the low inductance in order to maintain that bus voltage. On this side, I've already got an inductor there. So adding nanohenries or tens of nanohenries doesn't really matter. So this is where parasitic PC board inductance isn't important on the current loop side of the layout. So let's look at these devices, these GaN devices, and especially the surface mount. We only offer GaN in surface mount packages because we need this low loop inductance. Inside of a package, you have a wire bond. Here's the die, and here's another wire bond. And then the return path, this is showing a cross section of a transistor, GaN transistor, mounted on a layer. Here's the top layer in kind of yellow color, and then the purple color is layer 2. If I have my transistor current here, drain current, return on layer 2, I get a very thin layer, just like we looked at on the gate drive. Remember that. This gives me a very low overall inductance. So I could lay out my entire circuit this way, but I might run into one problem. So here's what we were just looking at, right? This transistor, it's expanded here to see a little bit better what's going on. The low side Q2, I have thermal vias that allow heat to escape to the back side of the board through the device. a whole bunch of them, like 100 and 130 vias here. That's how I get heat out, and these are ground connected, so no problem. What about Q1, the high side transistor? Now I have a problem. I need to get heat out of it, and that means I need the same set of thermal vias here. Where am I going to route those? I have to cut right through my return plane, which creates a hole, right? I can't run my return through the middle of a 400 volt switch node. So I need to make some compromises on my layout with these bottom side cooled devices. So if I didn't have to make the cutout, I'd have a very low 2.8 nanohenry loop inductance. But when I make this cutout, I now create a lateral path, and I end up with a much higher inductance, a factor of 3 higher. This can make it challenging. You can still make this work, but if I want the lowest inductance, the highest performance overall, I go to a different approach. I use a top-side cooled package. You can see that here. So now the thermal path comes out the top, and I can now optimize my layout with no vias. And don't forget, thermal vias are not cheap, right? Every drill hit costs money. So if I've got hundreds and hundreds of vias, that's not free. So let's look at what you get then is a layout that gives you optimized electrical layout, lowest possible loop inductance, and I can independently optimize my thermal path, get heat out of the devices through various means. Either direct soldering heat sinks, I can use bonded heat sinks, or I can use thermal interface material plus a clamp and so on. So the other key benefit here is now I free up the entire backside of the PC board for other circuits. I don't have to worry about noise because it's shielded by a ground plane across the entire circuit, and there are no vias poking through with noisy signals. That helps me to improve density. All right, so I think we covered those 5 key points I talked about at the beginning. Quick summary here is make sure you pay close attention to the peak current limits of GaN, especially at high temperature. I'll talk more about that particular topic in the common mistakes of first-time GaN users in this video series. Make sure that the gate drive circuit will supply the correct current, the full current. Don't hold back. You want to drive GaN as hard as you can all the time, just to make sure that you never run into a condition where it isn't fully on. Use the return plane under the gate drive circuit to provide the shielding and good return path, and use that vertical loop that we just talked about in the commutation loop in order to minimize inductance in that. And finally, the top-side cooled packages help you then separately optimize, independently optimize the electrical and the thermal path. Hopefully this will help you get started with your first GaN design, and take a look on the website for additional videos on these topics to help you with your design.